Okay, so the recording is in progress now, so please start.
Thank you. Yeah, I'm going to talk about a project that is published by now. It was published last year, joint work with Fatemeh, Mohammadi, and Alfredo, Nájera, Chávez, and a bit of an outlook of what's going on next. It's not going to be explicitly about Lie algebras, but maybe applications that you can also get from the algebras, and well, yeah, about the cluster structure of the Grassmannian. So my motivation comes from toric degenerations. I should maybe check the participants. Probably everyone is very familiar with this subject, but let me just quickly go through it. So if we have a toric degeneration of a projective variety, that's going to be a flat morphism to some affine space whose generic fiber is isomorphic to the projective variety we started with, and the special fiber is some toric variety. And most of the time I will be thinking about degenerations of this form. So we have an embedded projective variety, equations defining it, and the equations are deformed by the parameters of the affine space. So this here, for example, I mean, it's if you think of setting t equals to 1, this is a projective variety, and if t goes to 0, the equation defining the fiber is a binomial, so it's a toric variety. Now, one question I'm interested in general is how different toric degenerations of one projective variety are related. Like they sure capture some information of the projective variety that is just preserved throughout the family, but more generally, I'm interested in this question, and also in this particular talk, this will be kind of the leading motivation behind. So my two favorite constructions of toric degenerations are from Valuations and from Grbner theory. So I will quickly go through, just set up my notation here if you like. So if I have a graded algebra and domain, I will now be working with the homogeneous corner ring of my projective variety rather than the variety itself. And I have a full rank valuation. So the image of my valuation goes into a totally ordered abelian group. So a lattice with the lexicographic order, for example. And I require here that the image is a finitely generated monoid. I don't know why I really prefer the word semigroup, so I keep calling it semigroup, but the image is indeed a monoid. And I require the rank additionally to be of the cruel dimension of the algebra. So in this case, as many of you know, we can construct the toric degeneration of the projective spectrum of A, whose special fiber is a projective toric variety, and the normalization of this not necessarily normal toric variety is defined by the Newton-O'Kunkov polytope. So that's how we get toric degenerations from valuations, roughly. And a very important notion that I will need here is the one of a Kowalski basis. So a set of algebra generators of A is called the Kowalski basis for the valuation if the valuations of these elements generate the image or the value semigroup. Okay. So very brief also the how degenerations work from the point of view of Grbner theory. So here we now will be working with homogeneous prime ideals in some polynomial ring. And we can consider initial forms of polynomials or initial ideals of polynomials by just fixing some weight vector for all the variables. And instead of considering all the polynomial, we will restrict our attention to those monomials that have minimal or maximal weight. I prefer the maximal weight convention, but right now I'm not sure. Actually, I think in this talk it's all written with the minimal convention. So now all these weights in R to the n that we can choose, we have a particular preference for those weight vectors that give us initial ideas that don't contain monomials if we're looking for toric degenerations. And this part of R to the n is called the tropicalization, and it's indeed a fan. So if we find a weight vector inside the tropicalization whose initial ideal is binomial and prime, so toric, then we can construct a flat family of algebras, or a flat family of projective varieties with a generic fiber, the projective spectrum of our algebra, and the special fiber, the projective spectrum of the quotient of the polynomial ring by the toric ideal. So this in general is a non-normal toric variety. So it's a Gröbner toric degeneration. And these two concepts are closely related. You can swap from one to the other if you like. So if we start with a positively graded algebraic domain and with a valuation that is a full rank and finitely generated value semigroup, so that we have a degeneration following Anderson's construction, then we can kind of jump to the tropicalization of a certain idea. So we can construct an isomorphism of the algebra, an isomorphism of graded algebra between the algebra A, some presentation of it, such that the toric variety associated to the Newton-Kunkov polytope is isomorphic to the normalization of the toric variety we obtain from a certain point in the tropicalization of this ideal. Or more precisely, the value semigroup is isomorphic to this, semigroup algebra, this toric quotient. Okay, so well, let's go over quickly maybe over the ideas here. The main idea of the proof is to fix the Kowalski basis.
Lara, I'm sorry, could you please repeat what's the notation for NOR, the upper index? This denotes the normalization. So the projective spectrum of this toric algebra is usually or more likely a non-normal toric variety, projective toric variety. But on the left-hand side, the toric variety associated to a polytope will always be normal. So the right-hand side, the normalization of the right-hand side is the toric variety associated to this polytope. Okay, thank you.
You're welcome. Thanks for the question. Yeah, and feel free at any point to interrupt me for questions. Okay, so how do we get from the valuation to the Gröbner degeneration? Well, at this point exactly, we need the notion of a Kowalski basis. So we fix a set of algebra generators in A that are a Kowalski basis for the valuation, and take those to define this projection such that the kernel here, J, will give us the presentation of the theorem, this presentation. And so the polynomial here, polynomial ring here, might have non-standard grading, so that this actually is an isomorphism of graded algebras. Okay, so and then there's an algorithm how we can construct a weight vector associated with this valuation inside the tropicalization. In fact, there will be a whole cone inside trop J that contains such weight vectors that have the property that the initial ideal of J with respect to this weight vector is toric if and only if the value semigroup is finitely generated. And as we had as an assumption here that the value semigroup is finitely generated, well, by construction of this W, we will find the toric ideal associated to a point in the tropicalization. And the trick to construct this weight vector is also a standard one. All we need is really an order preserving projection from Z to the D to Z. So Z to the D is the codomain of the valuation. And all we do is really consider the valuations of the Kowalski basis elements and one by one project them onto Z to get a weight. Then we get a certain set of finite conditions coming from a Gröbner basis, for the idea J, that ensures that this weight vector we obtain by projecting the valuation actually gives us the right initial idea. Okay. So
this order preserving projection is like this Calderon.
Yeah, exactly. It's the standard construction of, I think, David Bayer in his PhD thesis, and then Calderon uses it. And so whenever you kind of want to connect valuations or a grading of higher rank with a Z grading, a Z to the N grading, with a Z grading, you need some kind of projection of this form. And
they exist because we have like a finite list of conditions essentially that are given by a Gröbner basis for the idea. Yeah. Okay, so right, so okay, great. So this result now tells us, well, whenever we have a full rank valuation with finitely generated value semigroup, there exists an ideal whose Gröbner theory contains the same information, or contains at least a cone that gives us the same toric degeneration. But yeah, like being interested in more than one toric degeneration at the same time, it's a natural question to ask if there's one ideal that works for all valuations. Like this, of course, the question is a bit too broad and a bit too vague, but in the applications with the Grassmannian, we kind of restrict our attention and make the question more precise. Okay, so before moving on to the Grassmannian, one last definition I want to recall is the one of adapted bases. So any valuation defines a filtration on my algebra where the filtered pieces, the subvector spaces are just given by all the elements of the algebra whose valuation is bounded by a certain value. A vector space basis of the algebra is adapted to the valuation if the intersections of the bases with these subvector spaces still are bases for all the vector spaces, all the filtered pieces. And this is a key ingredient for all the following constructions. Okay, maybe I will pause for a second because then I will continue with the Grassmannian if there's any questions or doubts. Okay. So then let's move on to the Grassmannian, and in particular its cluster structure. So I will be studying the homogeneous chordate ring of the Grassmannian, or with respect to its Plucker embedding, or the Plucker algebra. And it's well known by now due to results that were first written up by Scott, that for every k and n, this Plucker algebra is a cluster algebra. So very briefly, that means it is recursively generated by maximal sets of algebraically independent algebra generators, which are called seeds, and whose elements will be called the cluster variables. And there's an operation called mutation that creates a new seed from a given one by replacing exactly one element. So, for example, if we look at the Grassmannian 2,4, this is the Plucker algebra. So we have 6 Plucker coordinates indexed by 2 element subsets of 1, 2, 3, 4, and 1 3-term Plucker relation. And we can visualize this algebra by drawing all the triangulations of an n-gon. So this triangulation of a 4-gon has 5, one diagonal and 5 sides that correspond exactly to 5 out of 6 Plucker coordinates, and they form an algebraically independent set. The Plucker coordinates associated to the boundary cannot change, so they will be called frozen. They will always be part of a triangulation, but the diagonal can change. And so we refer to those as the mutable cluster variables. And then we can change the diagonal and get a new Plucker coordinate, the missing one, the P24, that can be expressed as a Laurent polynomial in all the Plucker coordinates of the left side. So this is just a toy model for a cluster algebra to have all the definitions straight. Okay. So toric degenerations can also be obtained from cluster algebras. So in this case, toric degenerations of the Grassmannian can be obtained, and there is one such for every seed. So in the case of the Grassmannian 2n, for every triangulation of the n-gon. And the way how it goes, there is through principal coefficients at a seed. That's a construction. It's like a combinatorial construction due to Fomin and Selewinsky, how you can deform a cluster algebra by adding as many additional variables as you had variables before. So if n is the number of my cluster variables in one seed, then the cluster algebra with principal coefficients lives inside the ambient field of the cluster algebra, which is the rational functions of the variables of any given seed. But the coefficients are now polynomials in the additional variables. And under some extra assumptions that were all satisfied for the Grassmannians, this cluster algebra with principal coefficients at a given seed is a free CT1 to Tn algebra, and it has a specific basis called the theta basis that was introduced and studied by Grosecki, Kiel, and Kontsevich. So this theta basis, it's worth mentioning here that is actually independent of S. So whatever seed you pick, you will get different cluster algebras with principal coefficients, different deformations of the first cluster algebra, but the basis, they all share the same basis. Yeah, and then moreover, if we start with the homogeneous coordinate ring of a projective variety, then as our cluster algebra, as will be the case for the Grassmannian, then the cluster algebra with principal coefficients defines a toric degeneration of X to some toric algebra, the toric projective variety that I will denote by X as 0.
Lara, I'm sorry, may I ask a question?
Sure.
So what is the relation between A and AS prime?
Yeah, so AS prime is a deformation of A. So I wanted to avoid the definition because it is quite combinatorial and well, a bit technical, but if you would like also in the end, maybe at the end of the talk, I can explain it a bit more. But yeah, so just the idea is that this A prime S is also a cluster algebra that is constructed from data very similar to the one that we use for the cluster algebra A. So at every seed of A, we will introduce an extra layer of variables that are these T1 to Tn that we will not use for mutation. They will just be frozen variables that we just carry along, but they will intertwine or deform the exchange relations that we get. So for example, for the Grassmannian 2n, maybe I should, okay, on the next slide, I have an example. Maybe we can go to the example.
Yes, but may I ask one more question here? So the
oh, now I'm frozen. Sure.
Right, you're frozen as well.
So
I can hear you again.
Yes, can you hear me?
Yes, yes.
Yeah, so my question is, what is the relation between the algebra A and variables X? So is A a quotient of the something or subalgebra or something or what?
Yeah, let me quickly share another slide that I
Sure.
Here, then I think it will become clear. Let's see if it works. Maybe I have to stop share again first. Stop share and share this one. Okay, yeah. Does it work? No, it's the same as before, right?
We can't see your screen now.
Okay. Then.
Okay, now we can see it.
No. Okay, great. So yeah, so this is a baby example of a cluster algebra as it is constructed recursively by this mutation procedure. So usually a seed is a collection of variables plus some combinatorial data that is here in terms of a quiver, so the A2 quiver. And all these steps here, these arrows, correspond to the mutation procedure that, for example, passing from this
Lara, I'm sorry,
to the...
is it possible to make it full screen?
Sure. Here we go.
Yeah, thanks.
Yeah, okay, so yeah, so exactly. So passing from this seed with the variables x1 and x2 to this seed corresponds to the mutation in direction 1. So we replace the variable x1 by this binomial of the variables we had before, and so on. And if we go all along, then at some point we come back in this case, and these are all the seeds of my A2 cluster algebra, and the cluster algebra itself is defined as the subalgebra of the field of rational functions in my original variables x1 and x2 that are generated by exactly these elements I collected along the way. And now, let me see if I can go to the other slide. I think I have to stop the full screen. And now I also have an example of the cluster algebra with principal coefficients in this case. That is this one. So we start in our original seed by extending the combinatorial data and the set of variables by exactly as many t parameters as we have x's, and where the quiver is extended in this way that we introduce new vertices and new arrows, always an arrow from a new vertex to the corresponding old one. And then we can follow the same mutation rules, with the exception that we will never perform mutations at these new vertices. So we will keep just the mutation pattern that we had before. And the cluster algebra with principal coefficients at this seed is now the one generated by all the variables that you can see here in the original vertices. So we had like three variables that are not x1 and x2 in the original cluster algebra, and in this case, these three elements, these three cluster variables, are deformed by the t1 and t2 parameters. And the new cluster algebra is generated by all these by these elements x1, x2, t1 plus x2 over x1, etc. Inside we have coefficients that are polynomials in t1 and t2.
And can you hear me?
Sure, yeah.
So just about this degeneration, so it's a flat family, right? It's a flat degenerate, and it's over an. So
yes.
And you say that the generic fiber is isomorphic to x, but so all fibers outside of 0 are x, or just some of them?
Well, the base here is now, in this example, for example, we have the base is A2. So we can set all t's to 1. That will give us back the original cluster algebra and hence the original variety.
Okay.
We can set all the t's to 0. That will give us a toric algebra and the toric variety. But now we have some in-between fibers by letting just one t vanish, or and so on. And those are deformations that lie somewhere in between the projective variety and the toric variety.
Sorry, but generically, the other fibers are still isomorphic to the fiber 1, 1.
Yes, exactly. As long as all the entries of your point in the affine space are non-zero, you will get something that is isomorphic to the original.
Oh, so only on the coordinate axes we have something else.
Exactly. Yeah.
On the coordinate subspaces.
Yeah.
Okay.
Yep.
Okay, thanks.
No, you're welcome. Let me go back to the other slides. Yeah. Here. Okay. Let's see, I think I have to wait a second until it works. Yeah. Okay. Exactly. Yeah. So so maybe one more thing. It's not only a flat family, but actually free, because we have this theta basis throughout the whole family. So so it's important to remark at this point that we have such a degeneration for every seed of the cluster algebra, such a family, and it will be different for different seeds, but all of them have the same theta basis. So as a vector space, all these algebras with principal coefficients are isomorphic to the direct sum of all the theta basis elements. Okay, neglecting the coefficients that here, this is a statement over CT1 and Tn. Okay, so great. So that's how we get toric degenerations from the cluster algebra perspective. But there's one more thing we can do with cluster algebras that's pretty cool. That's called universal coefficients. So the idea is now, for simplicity, I will assume we have finitely many seeds, so that all these results and statements are a bit more tractable, but these constructions work more generally. And the idea is that we deform the cluster algebra not with respect to only one seed with the principal coefficients, but with respect to all seeds at the same time. So we have a cluster algebra with universal coefficients that now lives still, well, in the field of rational functions with as many variables as I have in one seed. But the coefficients can now be in a polynomial ring that is way larger, that has one variable for all cluster variables. So in the A2 example, we would have now 5 t parameters instead of just 2. And as this is, roughly speaking, this is really introducing all the t's that we find in different principal coefficient degenerations at the same time. So we have a specialization map that is induced by just the projection of the big polynomial ring to the small polynomial ring. And it gives us a map from the cluster algebra with universal coefficients to the one with principal coefficients at any seed by neglecting the t parameters that do not correspond to the variables of my seed. So the upshot of this construction is that this cluster algebra with universal coefficients knows all the toric degenerations we can get from principal coefficients.
Lara, I'm sorry.
Downside.
Could you please elaborate a bit on this statement? So what does it mean it knows all toric degenerations?
So by specializing the t parameters here to different values, let's say 0 and 1, we can obtain, exactly by these maps, we can obtain all the cluster algebras with principal coefficients. And if we go one step further here and now specialize all the t parameters that survived the specialization map to 0, we get the semigroup algebra that defines this toric degeneration associated to a seed. But now we have these specialization maps for the cluster algebra with universal coefficients, not just to the principal coefficient algebra with respect to one seed, but with respect to all seeds. So specifying the t's, the parameters, specializing all the t's that do not correspond to one fixed seed to 1 and all the others to 0, we get the toric semigroup algebras that define the toric varieties of the principal coefficient degeneration.
Sorry, maybe a silly question. So you said that the algebra with universal coefficients covers all the algebras with principal coefficients. What degree of freedom did we have when defining the principal coefficients construction? So you say there are many different ones. Where do we get different ones from? So I don't quite.
Sure, yeah. So we get a different principal coefficient algebra for every different seed. So for example, for the Grassmannian to n, we will have one for every triangulation of the n-gon. And a priori, they will all define different toric degenerations of the Grassmannian. In the end, there's going to be many isomorphisms, but that's kind of
okay. So for
another
this
story.
For this quiver diagram where you had with the seeds, it actually can be for the same cluster algebra for the Grassmannian can be drawn in many different ways. Yeah. And after that you add the t's.
Exactly. So in the quiver diagram there was 5 different quivers. 2 of them were isomorphic in the end. So for the 5 different quivers, we get 5 different degenerations, 5 different principal coefficient algebras.
And 5 is the Catalan number.
In this case, yes, exactly. Yeah. Let me see if I have I think here there's an example. Yeah, okay. I mean, this example is, well, maybe both enlightening and misleading. So for the case of the Grassmannian 2-4, where we have two triangulations of the foregone, we have 2 different ways to define a cluster algebra with principal coefficients. So in the case where the triangulation has diagonal 1, 3, we introduce one parameter T13 that will deform my my Plucker relation in this way. So it will introduce this coefficient T13 in front of one of the 2 terms that share the same sign. In the second case, we would have a parameter T24 that would actually appear in front of the second term. So these are the two ways that we get toric degenerations. If we cancel, or if we set the t equal to 0, we get two different but isomorphic binomial ideals. And the cluster algebra with universal coefficients, writing it out in this kind of presentation, well, it just has both parameters, t1,3 and t2,4, and well, they are exactly where they would appear in the principal coefficient algebra, but now we have both of them at the same time. So by varying the t's here, we recover the two different binomials that we got from the two different principal coefficient constructions. Does it make sense?
Yeah, thank you. Just in the general case, you said you have to triangulate which polytope, the hypersimplex or something else?
No, just so for the Grassmannian 2n, we have this nice description in terms of triangulations of an n-gon. For other Grassmannians, there are combinatorial substitutes, but nothing is as satisfying, as I would say. So the Grassmannians, so there's only a short list of finite type Grassmannians where we have finitely many seeds.
Okay.
So these are 2n, 3,6, 3,7, and 3,8. And beyond that, we have infinitely many seeds. And yeah, the combinatorics used for all the seeds are certain quivers, but there's no nice geometric realization of any kind of seed for arbitrary Grassmannians.
Okay, got it. Thanks.
Okay. Yeah. Let's see what else is on this slide. Yeah. So I think this is actually a repetition, or not really. So there's one nice thing that we can do with this principal coefficient degeneration. So Fatemeh and Zalevinsky, they introduce these principal coefficients because it's a way to introduce a grading, a z to the n, a z to the d grading, on a cluster algebra. So what we can do with this grading, it's not hard to see that this grading actually is a valuation, or defines a valuation on the cluster algebra, where it's called the G vector valuation, because G vectors are these grading vectors that Fatemeh and Zalevinsky introduced. So for every seed, we have a valuation that is closely related with this cluster algebra with principal coefficients that simply sends a cluster variable, or more generally an element of the cluster algebra, to its G vector. And this is also the connection of the principal coefficient degenerations to degenerations induced by evaluation. So these valuations are of full rank, and they have finitely generated value semigroup, so that we can recover the toric degenerations also from Anderson's construction using exactly this valuation.
Lara, I'm sorry, what is D here?
D was the cruel dimension of the algebra. So it should, I got a bit of a problem with notation. Usually I call the number of elements in one seed n, but so D is the
n choose k.
No, it's the dimension of the Grassmannian. So n times
n times k.
K times n minus k plus 1. Yeah.
Thank you.
Yeah.
So the image of the valuation is always the whole space, and that's what you mean by full rank valuation, right?
With full rank, I mean that the image as a vector space generates the whole space. Right? Because it's
The dimension of the image is D.
Exactly. But well, the image is not a vector space. But if you take the vector space generated by the image, it's exactly, it's full dimensional. Yeah. Okay. Yeah. So maybe one more thing to say: this theta basis that appeared, that was a vector space basis for these principal coefficient algebras, is not a big surprise that it is an adapted basis for this valuation that comes out of the construction. And yeah. Okay, yeah, and this middle part here is just the statement that I mentioned before, that we have these projections, these coefficient specialization maps from the cluster algebra with universal coefficients to all the cluster algebras with principal coefficients. But here I just spelled it out for the particular case of the Grassmannian Kn. So in particular, to sum up, like having this connection from the principal coefficient degenerations to a full rank valuation, we can now apply this motivating theorem and get some ideal representing the cluster algebra with principal coefficients. Or, well, no, representing the cluster algebra, so the Plucker algebra, but this ideal may be different for different seeds.
Lara, I'm sorry, one more question. So what is your S mute?
Yeah. So S is always my notation for a seed, and mut refers to the mutable cluster variables in there. So remember, for the foregone already, we have 4 cluster variables that correspond to the boundary that will be part of every seed, and we may as well carry them along here, but they will not have any impact on actually deforming the cluster algebra. So for simplicity, I will always restrict my attention to the mutable cluster variables, like in this example. I only have a t parameter for the Plucker coordinates that correspond to diagonals of the n-gon, because the others, they would not actually appear in the exchange relation.
Right, and what is it in general for general K and N?
For general K and N,
yes,
we have right. So we have a quiver that looks like a matrix that has k rows and n minus k columns and one more. So that's this D, k times n minus k plus 1. And along this quiver, the plus 1 and the first row and the first column, the last row, all these variables are frozen. So we will have mutable variables k minus 1 times n minus k minus 1 many, and the rest will be frozen.
thank you.
Sorry, and this specialization map from the universal to the principal. So what you always do is you replace each t with a rational function in t's, or can it also depend on the x's?
So I mean, these algebras,
yeah,
they are both contained in this field of rational functions in the x's.
Yes.
But they have different, they have coefficients in these different polynomial rings.
Yes.
And the projection from the big polynomial ring to the small polynomial ring, by just sending all the t's that I want to get rid of to 1 or to elements of the,
so it's always that simple.
Yeah, exactly. Yeah.
Oh, okay. Okay.
Yeah, it's really well behaved. Everything is really nice. In particular, we have finitely many seeds, where the situation is.
So because capital N is like the number of all the seeds that may appear, and small n is the seeds that appear for a certain seed, starting seed, right?
Okay, so capital N is the number of all the mutable cluster variables that I find in my cluster algebra. It's a bit misleading because in the example of the A2 quiver, we have 5 cluster variables, but we also have 5 seeds. But in general, these are different numbers. And so the number of cluster variables is the capital N, but all cluster variables, like running through all seeds and collecting all the cluster variables, that's capital N. And yeah.
So here, capital N and small n coincide.
In the Grassmannian 2.4, yes, exactly, yeah.
Okay.
Oh, is that a thing for Grassmannian 2n? No, but for general Grassmannian 2n already it will not coincide. Like one is the Catalan number and one is the number of diagonals. So one is n choose 2 minus n, and the other is the Catalan number.
Mm-hmm.
Yeah. Okay. So so exactly, coming back to my original question, my original motivation, I will now make it a bit more precise and I want to understand these different ideals J that I get out of these different ways to present the algebra that is adapted to the valuation, or corresponding to the valuation. And I want to know how all of these are related, and what this very nice algebra with universal coefficients, how that can be understood from the point of view of Grbner theory, because it very nicely captures the information of all these toric degenerations at the same time. Okay, so in order to get started, I need a bit more of notions from Grbner theory. One object that I will rely on is the Grbner fan. So this was defined by Mora and Robiano in the 80s. And it is for a homogeneous ideal, J inside a polynomial ring with n variables. It's all of R to the n with a fan structure defined by the initial ideals. So two weight vectors lie in the interior of one cone if and only if they give me the same initial ideal. So from now on, I will adapt my notation and talk about initial ideals with respect to a cone, which just means the initial ideal with respect to any representative in the relative interior of the cone. And for the quotients of the polynomial ring by initial ideals, I will also adopt the notation AC. So A is the quotient of the polynomial ring by J itself, and C denotes some cone in the Grbner fan that can be a maximal cone or of higher codimension. Now, one more ingredient that we nicely get from Grbner theory here is if we fix a maximal cone in the Grbner fan, then the initial ideal will be generated by only monomials. Every such maximal cone defines as a vector space basis for the algebra itself, whose basis elements are indexed by monomials that are not contained in the monomial ideal. So those bases are standard, will be called standard monomial bases. And for every maximal cone, the standard monomial basis is a basis not only for the algebra AC, the quotient by the monomial ideal, but also the algebra itself and all the algebras that I get from faces of the cone C. So these are all deformations of the algebra A, and they all have, as vector spaces, they're all isomorphic with a basis given by the standard monomials. Okay, so just an example for people that might have not seen this before. If this is my ideal J, a homogeneous ideal in 3 variables, the Grbner fan will be all of R to the 3. I have a linear subspace here, which will always be the case for homogeneous ideals. It consists of all the elements, the weights that leave my ideal invariant. It's called the linearity space. So it's generated by the degrees that make my ideal homogeneous. And besides that, we have 3 maximal cones that correspond to the 3 monomials in my trinomial and their intersections that whose initial ideals are exactly given by, well, the terms surviving that correspond to the adjacent maximal cones. And then the standard monomial basis, for example, for this purple cone here, is given by all the monomials that are not dividable, that cannot be divided by x2, x3 cubed, which is the generator of the monomial idea. Okay, so now I want to upgrade the usual Grbner degeneration by considering a degeneration not only with respect to a single point in the Grbner fan, a single weight vector, but a whole cone. And I will do this for a maximal cone. For simplicity, you can also choose a cone of higher codimension. And what I will do is that I would choose representatives of the rays, primitive ray generators of my cone, and do the Grbner theory construction for all these points at the same time. So formally, that means I have to consider for a polynomial in my ideal this vector of minima, where I always take the dot product of all my ray representatives with the exponent vectors appearing in the support of my polynomial. And then I will lift my polynomial to an element in the polynomial ring with coefficients in another polynomial ring in t parameters, one t parameter for every ray. And now so either, I take my polynomial f and I don't evaluate just on the x's, but I introduce also monomials in t's. So for every variable xi, I will multiply it with a monomial in t's that is given by the product of the matrix whose rows are my ray representatives times the standard basis element. And in the end, what will happen is that the support of this polynomial is still the same. So the support in terms of the x's, and every monomial x to the alpha will be multiplied by a monomial in t's whose exponent vector is exactly the matrix R times the exponent vector minus this vector of minima. Okay. So then the lifted ideal is the ideal generated by all the lifts of elements of J, but it is actually generated by, it's finitely generated by the lifts of any of elements of any Gröbner basis. So in the example, I fix, for example, this purple cone.
Lara, I'm sorry, can you please get back to the previous slide?
Yeah.
So once again, this f tilde is an element of this large ring, right?
Yeah.
So the vectors R1 up to Rm. So are you fixing them, or you somehow use all of them, or what?
Yes, I fix them. But so this is a choice I make, but the result is independent of the choice. So what I do here is first I quotient out by this linear subspace for simplicity.
Okay.
And then because then the cone in the quotient, the image of my cone is actually a strictly convex cone. So I have well-defined primitive ray generators. And then I just take representatives in the big ambient space of these primitive ray generators. And those are my R1 to Rm.
Okay. Okay, thank you. Mm-hmm.
Yeah, so maybe this is actually good to look at it in the example. So in this example, the Gröbner fan itself, its support is R3, all of R3. But because of this linearity space, I can restrict my attention to this two-dimensional picture where I just realize the quotient as I realize the quotient as the intersection with the subspace where the third coordinate is equal to 0. And so in this subspace, I have a two-dimensional cone that is strictly convex in the quotient, and its primitive ray generators are 1, 4 and 1, minus 2. So 1, 4, 0 and 1, minus 2, 0 are representatives of the primitive ray generators in R3. So this is my matrix of rays. And this is the lift. So what happens here is that every coordinate xi, I multiply it with the monomial in t's, whose exponent vectors is now the columns of my matrix. So the rows of the matrix correspond to the rays of the cone. So they have one entry for each variable xi. So and the columns are all the weights appearing for one fixed variable. So T1, T2 is the monomial that appears in front of x1. T4, T2 minus 2 is the one of x2, and so on. And then in the end here, this is this vector of minima. So if I fix, for example, T1, I have to compute what is the minimal dot product of my vector 1, 4, 0 with the exponent vectors appearing in the support. And then the minimum is obtained at 2 points at these two monomials, and it's 4. So I have this exponent minus 4, just introduce a sign. So if I compute, this is my lifted polynomial. So I have the same number of monomials as before, just that every monomial in x's now has a corresponding monomial in t's. just one monomial. Is there a question?
No, more of a comment. Sorry, go on.
Okay, sure, go ahead.
But sort of this whole construction, it depends on the fact that there is a single monomial in F, which will occur in the initial parts with respect to each of the R's, right? So I mean, if you chose the R's in your matrix to be arbitrary vectors, this will sort of not work.
Sure. I mean, yeah. If you,
there is a single monomial, which the sort of grading is mu of F, with grading mu of a monomial which occurs in the initial parts with respect to each of the R's. And this is why the definition works.
Yeah, so I mean, the definition is chosen in such a way that it is compatible with all the Gröbner degenerations of that I can obtain from the cone C and its faces. If I take now an element of a reduced Gröbner basis, I will see this phenomenon that there is a single term surviving, which is exactly the initial monomial with respect to the interior of the cone.
Well, yeah, it has to.
Yeah, and I mean, if I have an element of a Gröbner basis that is not element of the reduced Gröbner basis, this might not work. And
right. So, if you write out this f tilde, it might not have a unit coefficient anywhere. So, right. Not necessarily.
In more than one, I mean, yeah, it will have unit coefficients, but it could have more than one. I mean, for sure, the initial form of any, well, okay, if I set now all the t's to 0, for sure I will get an element that is in the initial ideal, but it might not be a monomial. It might be a combination of monomials.
That's not, but is there, so if you take these R's, right, these R's, which are your spanning vectors of the cone, and for each of the R's, you have an initial part. For an arbitrary F, you have its initial part.
Yep.
Is it true that there is a monomial which actually occurs in each of these initial parts? So, and this is not necessarily true, right?
So if I have one polynomial, it has one initial monomial that belongs to the interior of the cone.
For different points in the maximal cone, the initial monomial may be different. It will always rely in the initial ideal, but for a fixed polynomial, it may be different.
Right. Yeah. Yes.
So how do you know you get a unit coefficient somewhere?
Well, I don't know for arbitrary elements of the ideal.
Okay, so it's not true for arbitrary.
Yeah, exactly. No, that's the trick where you have to use the reduced Gröbner basis. But so there we know everything works. We get exactly what we expect: a unique monomial with coefficient, with its unit coefficient, and it's going to be exactly the monomial that is the initial form, the initial monomial. Yeah.
Okay, thank you.
Yeah, exactly. And then the rest, I mean, if you choose to set some of the t's to 1 and not all of them to 0, you can kind of interpolate between all the initial forms that are corresponding to the faces and the interior. But all this example works super nicely here because for ideals that are in the hypersurface case, where my ideal is just generated by a single element for principal ideals, where the generator is a reduced Gröbner basis. So I know all this will happen, but in general, I will have to be careful and choose elements of the reduced Gröbner basis.
Lara, by the way, in the formula for F tilde in the second line, do you really have a minus?
In the second line, yes. So the typo is here. This should be a minus.
Oh.
Yeah.
Okay.
Thank you. Yes, I'm sorry. Yeah, I corrected it in all these places, but I forgot this one. Yeah. Okay. So any more questions or comments about the example or the construction? Cool. Okay, so then let me move on and present the reason why we do this construction. So by a tilde from now on, I will denote the quotient of the big polynomial ring by this lifted ideal. And well, recall that a tau was my notation for the quotient of the small polynomial ring by any initial ideal with respect to a cone tau. And then the theorem is that, as expected, a tilde is a free CT1TM module with basis BC. That was the standard monomial basis for the cone C. So yeah, to be precise, a tilde should carry C, and more precisely the selection of rays in its notation, but I'm dropping this for simplicity. Because the algebra A tilde for different choices of R's, they are isomorphic. And yeah, so in particular, pi defines a flat family. The generic fiber is the spectrum of A. And for every phase of my cone C, there are points in the base such that the fiber over this point is the spectrum of these algebras A tau. So in the example, A tilde is the quotient by this lifted polynomial, the ideal generated by this lifted polynomial. And a quite obvious corollary, just to emphasize the relation with toric degenerations, is the following. If I now consider the intersection of a maximal cone with a tropicalization, that will be some fan sigma. And if in this fan sigma, I can find some cone whose initial ideal is binomial and prime, so to say toric, then the big family defined by A tilde contains toric fibers that are exactly the fibers corresponding to these over these points A tau. That will give me toric degenerations of A, and I can see all the toric degenerations in this family that correspond to faces, faces with toric initial ideals of my cone C. Yeah, and yeah, so that's the general part of the construction. And in this case of the Grassmannian, we wanted to see if there is any relation between these types of algebras A tilde and the cluster algebra with universal coefficients. So before I will state the theorem about this relation, I will quickly go back to the cluster algebra. So remember, cluster algebras are defined really recursively. There's no unique presentation that we get for a cluster algebra. But if the cluster algebra is of finite type, then we can simply present it by the polynomial ring of all cluster variables. So in the case of the Grassmannian 2n, for example, these are as many variables as the n-gon has diagonals. And then, moreover, there's a result in the book of Fomin, Williams, and Selewinsky that tells us that we can actually get this ideal J by saturating the ideal generated by all the exchange relations. So for the Grassmannians, I will now restrict my attention to the Grassmannian 2n and 3,6, also for the result, although it has been generalized already. For the Grassmannian 2n, this ideal J is exactly the Plucker ideal. And for the Grassmannian 3,6, all my Plucker coordinates are cluster variables, but there's two more elements that are cluster variables that are degree 2 binomials in Pluckers. Well, this ideal J36 is a bit bigger. It lives in a bigger polynomial ring than the Plucker ideal, but I can recover the Plucker ideal by eliminating the variables x and y. So here's an example of this ideal, a generating set for this ideal for the Grassmannian 3,6. So I find here all three-term Plucker relations. I find the binomial expressions for x and y in terms of Pluckers. And I have one more element that looks like a four-term Plucker relation where I have replaced x and y, where I have substituted parts of the monomials and Pluckers by x and y. But I mean, yeah, you can change this one. Okay, so then, oh yeah, sorry, one more ingredient before I come to the result, I'm sorry. It's just a little nice, like a side topic that appears here. That's about total positivity and totally positive ideals that I want to use in the statement of the result. So if I have an ideal that lives in the polynomial ring with real coefficients, like the Plucker ideal, then this ideal is called totally positive if the intersection, or if it does not contain any polynomial with only non-negative coefficients or only positive coefficients. And given this definition, if I have a totally positive ideal J, I can restrict my attention in the tropicalization even further by considering only those points, weight vectors in the tropicalization, whose initial ideal is also totally positive. So this definition of totally positive is, well, maybe not too easy to deal with, but there's another characterization that appears in work of Einsiedler and Tunkel, which is based on work of Handelmann, that tells me the following. So if I have an ideal in a polynomial ring with real coefficients, it is totally positive if and only if I can find some weight vector in R to the n such that the vanishing set of the initial ideal with, oh, sorry, this should be J. The initial ideal with respect to this weight vector contains a point in the positive orthant.
Lara, I'm sorry, in the definition, do you want to take non-negative real numbers or strictly positive real numbers in the first line of the reminder?
Yeah, I think it is equivalent. I chose non-negative ones because like this I greater or equal to 0 is still a semigroup. And that has some advantages when we thinking of generalization, but you might as well replace it with just positive.
So you
oh, okay, let's remove 0 from this set then.
Right, yeah.
I
see. Yeah. Okay, thank you.
Yeah, no, thank you. Yeah, this is yeah, very good comment. Okay, so a quick example just to sort these things out. So yeah, so the result of Einsiedler-Tunkel based on Handelmann's result tells us that this positive part of the tropicalization is a closed subfan of the tropicalization, which itself is a closed subfan of the Gröbner fan. And in our example, the initial idea, we found 3 initial ideals in the tropicalization that corresponded to these 3 binomials. The first one is not totally positive, well, that's easy to see. The other 2 are, and the easiest way to see this is maybe to apply this result by Einsiedler-Tunkel-Handelmann and see that we can degenerate both further or take initial forms of both so that just the monomial survives. And well, then this condition is obviously satisfied. Okay, so now I'm ready for the result regarding the Grassmannian cluster algebra and this Grbner degeneration. So if I will restrict my attention to the Grassmannians 2n and 3,6, and I will consider this ideal JKN that presents the cluster algebra with respect to all its cluster variables, then the following is true. There exists a unique maximal cone in the Grbner fan of this ideal, whose initial ideal is generated by all non-compatible cluster variables. So non-compatible here means these are products of cluster variables that never appear in a seed together. So for the Grassmannian 2n, this is generated by all products of cluster variables or Pluckers that correspond to crossing arcs in the n-gon. Another way to see this is that this initial ideal is the Stanley-Reisner ideal of the cluster complex, but I didn't want to introduce the cluster complex, so just as a side comment. Moreover, there's a canonical isomorphism between the algebra A tilde that we obtain by lifting the Plucker algebra with respect to this cone and the cluster algebra with universal coefficients, where the rays of my cone are now in bijection with the universal coefficients, which are further in bijection with the mutable cluster variables. then the standard monomial basis coincides with the basis of cluster monomials, which is in this case the same as the theta basis that I've mentioned before. So this basis that I get for for nice cluster algebras. And moreover, why I wanted to have the positive part of the tropicalization, if I intersect this maximal cone C with the tropicalization of the ideal, I obtain exactly the positive part of the tropicalization. So this is a very nice, quite special property. I still don't know a general criterion when this will be the case, but it is true for these special ideals JKN. And this means that we have a geometric realization of the cluster complex. So, okay, I'm mentioning it again. It's a polyhedral object or a simplicial complex that encodes the adjacency relations between seeds in the cluster algebra. So more precisely, the rays of the positive part of the tropicalization are in one-to-one correspondence with mutable cluster variables. The frozen ones will actually correspond to the linearity space. And the maximal cones in the tropicalization are in one-to-one correspondence with the seeds of the cluster algebra. And then all these correspondence is not just a combinatorial or polyhedral correspondence, but if we actually go down to consider on the Gröbner side, these toric algebras, these algebras corresponding to maximal cones in the positive part of the tropicalization, which turn out to be all toric in this case, then the projective spectrum of these algebras, the projective spectra coincide with the toric varieties that are obtained from the Newton-Acunkov polytope of these G-vector valuations associated with the principal coefficient algebra. And these results have been generalized. To mention a work of Ilton, Nájera, Chávez, and Treffinger that generalized for finite type cluster algebra. So now it's for the Grassmannian case, we now also know this result holds true for the Grassmannians 3.7 and 3.8.
And what about the other Grassmannians? So do you expect the claim is still true or not?
Yeah, that's a very interesting question that I think in 2 slides I have a bit of an outlook what you can still expect for general Grassmannians. Okay,
may I put the question in another form? So let's look at the second point. So is it clear at least that numerically the number of universal coefficients is exactly the number of rays of C?
Well, so we have one problem with general Grassmannians that already starts with this ideal J. So this ideal J, for now, it was for me the ideal presenting the cluster algebra with respect to all cluster variables. So quotient of a finite polynomial ring. Okay. If I have an arbitrary Grassmannian, I have infinitely many cluster variables. So there's like a bit of a problem there, because Gröbner theory for non-Noetherian rings is a bit of a more complicated issue, and I'm not even sure if I would want to go in this direction.
I see.
And yeah, so we cannot expect this to hold true if the cluster algebra is not finite type anymore. Yeah.
Thank you.
Yeah.
Will you give some example for at least for 2n? So just to see which maximal cone it is.
So I don't have it spelled out, but combinatorially it's really nice. So the rays of the tropicalization for the Grassmannian 2n are parameterized by partitions of the set 1 to n where of 2 partitions into 2 sets where each element contains more than 2 elements. And in this particular case, the partitions, let me think, they correspond to,
no, what?
Yeah, so,
Yeah, no, what I meant was just so when you have the Grassmannian 2n, this ideal JKN is just the Plucker ideal, right?
Yes.
And so this initial ideal considered in this theorem is some specific initial monomial ideal of the Plucker ideal.
Yes.
I mean,
yeah. So
we know a few of those.
Yeah, exactly. It's the nicest one. It's this non-crossing initial ideal. You know, there's a total order that for 3-term Plucker relations. I mean, if you would draw the numbers 1 to n on a circle, and then 3-term Plucker relations correspond to arcs or diagonals in this circle, and the initials picked out are always the ones corresponding to crossing arcs.
So you take two Plucker variables such that the diagonals cross, and you generate the ideal by these quadratic monomials. Right?
Yes, exactly. That's the generating set for here. Exactly. Yeah.
So it is the fact that they cross is more or less means that the Young tableau is not semi. So it's the same ideal that is generated by non-semi-standard 2 times 2 Young tableaus. Well, it kind of seems like the same thing. I'm not sure. Well, it just means that one of the numbers is less than the other, and the other, or no, oh no.
No, I think it's exactly not those. Well, elements that are not in the monomials that are not in the ideal, I think they correspond maybe to semi.
Okay, what I said is wrong.
I did this compute. Yeah, I think it's not the same. Yeah, I think it's not those. I checked this at some point when Peter asked me about standard monomials, like standard monomials coming from Young tableau and standard monomials in the sense of Gröbner. And I think they're not the same here. So maybe
they're somehow dual. I mean, you can dualize this semi-standardness in several ways. Maybe there's, or it's some principally new ideal, some different ideal. So
I mean, I don't know the relation with Young tableaus, but this is not surprising to get this idea. Like this is this very nice non-crossing initial ideal of the Grassmannian 2n. That, I mean, you can find it in like Gröbner basis literature on the Grassmannian. Then you will find this ideal. I think Sturmfeld wrote it down already, like in early 2000 or even in the 90s or something. Yeah.
Okay.
Yeah, but it would be a nice exercise to check what's going on with the Young tableaus to see if there's a relation. I think I did this computation once and I convinced myself that they're not the same, but maybe there's some like dualizing, as you mentioned, or something that you can make. You can apply. Yeah, I think I have this slide is just the reduced Gröbner basis for this case.
No, I actually think it's the same. I think it's more or less the same ideal, maybe for modular dualization. Well, we can think about it afterwards. Yeah. I think it's geometrically it's isomorphic. That's okay.
Yeah, but there's some. I mean, also the Gröbner cones of the Grassmannian 2n that intersect the tropicalization, they're all isomorphic as well, and all the initial ideals. So there's like it's so symmetric everything.
Okay, well, yeah.
Yeah.
Mm-hmm.
I think those cones in the Gröbner fam, they are parameterized by orderings of 1 to n, like all the possibilities to order the numbers 1 to n, and that will correspond to the labeling on your circle, and then you get the different notions of crossing.
Mm-hmm. Yeah, that's right. Okay, yeah, we can discuss this in more detail.
Yeah. Okay. I'm almost done. So yeah, this is just the reduced Gröbner basis for the ideal J36, just to give you an idea that the minimal generating set I had before is not enough. I need to add some degree 3 elements or this degree 4 element. And the first monomials here are the ones that lie in the initial ideal. And one observation to make is that none of them contain blue Plucker coordinates, which correspond to the frozen direction. So that's to be expected from the result. And then maybe the last, I don't know how much time you will give me, the last few minutes, I can say roughly what we can expect for arbitrary Grassmannians. So what still holds true from the stories I told so far from the point of view of cluster algebras is these valuations. So I can still construct principal coefficient algebras. I still have these G vector valuations, and I still have toric degenerations of the Grassmannian. So then I still have this motivating result that gives me a relation between the toric degenerations I get this way and maximal cones in the tropicalization of certain ideals. And the conjecture or expectation that I'm writing up right now is the following. So if I fix a seed of the cluster algebra Kn, then by this correspondence result, there exists a maximal prime cone in the tropicalization. The conjecture further states that it will be in the positive part of the tropicalization for an appropriate ideal J that is exactly obtained as I explained in the beginning of the talk. And moreover, if this ideal J turns out to be appropriate for two valuations, GS and GS prime, that correspond to seeds that are related by a mutation, then the corresponding tau cones, tau S and tau S prime, also share a facet. So we can kind of locally still have the results of the theorem before, just that in the situation of having infinitely many seeds, we cannot expect to have this global results where we can see cones for all seeds in some tropicalization or the positive part of some tropicalization. And yeah, so appropriate here means exactly that the value semigroup of the G vector valuation is generated by the images of these xi's here, so that I've chosen a Kowalski basis to get my ideal. For the Plucker ideal of the Grassmannian 2n, well, the Plucker ideal is appropriate for all seeds. There's no new result here. For the Grassmannian 3.6, I can already find some seeds that are combinatorially, they're parameterized by these Plavic graphs. I just want to put them in case someone is familiar. So there's already some pathological examples that I can find for the Grassmannian 3.6, where the Plucker ideal is not appropriate, and that's also part of the reason why we considered this bigger ideal for the result before. And conjecturally, the idea presenting a finite type cluster algebra with respect to all its variables is appropriate for all seeds. And I think this should also follow already by work of Ilton, Nájera, Chávez, and Trefino. Okay, that's it. Thank you very much for your attention. I'm sorry for going so long, and I'll leave you with some references.
Thank you very much.
Thank you.
So any questions? So I have some questions. Can you please go to the previous slide?
This one or the one before?
I think, yeah, this one. So could you please explain what do you mean that the Plucker ideal is not appropriate? So what does it mean?
Yeah, so it means in this case that, this motivating theorem from the beginning of the talk that stated if I have a valuation, then I can find a maximal cone in some tropicalization that gives me the same toric degeneration of my algebra, or of the Grassmannian in this case. If I take the Plucker ideal and consider its tropicalization, then there will be no maximal prime cone in the tropicalization that recovers the toric degeneration of the Grassmannian that I get from these two special seeds. So I have this relation here, right, between toric degeneration induced by valuations and maximal cones in the tropicalization of some ideal J. And this ideal, the Plucker ideal J36 here, does not work for all these valuations obtained from seeds for the Grassmannian 3.6.
Okay, I see. Thank you.
Yeah, but this slightly bigger ideal with these two extra variables works for all seeds in the case of the Grassmannian 3.6.
Okay.
Yeah.
Thank you. Further questions?
Well, I had a similar question to the one I asked, but now for n equal to 3 or k equal to 3. So if you go go back to the theorem.
Here.
So right. So well, when k is 3, the ideal is already larger, right, than the Plucker ideal. But so do I understand correctly that so if you consider this this initial ideal, for instance, the monomial initial ideal, so it will I think it will be just an initial ideal of the Plucker ideal plus like the additional variables. Is this true?
No, there's no variables in the ideas. It's generated in degree 2.
Yeah.
And and these, so for example, these monomials that are the leading terms here, or that are the first monomials in this list, they are all elements there.
Okay. So here, right. So could you say, so here this monomial, this distinguished initial monomial ideal is generated by these first summons, and that's it?
Plus the ones that I had on the other slide when I showed you the ideal. Yeah, here, exactly. So these two slides together, it's these monomials that are in the first spot here. They're just monomials of degree 2 in Pluckers, plus the other monomials in the additional elements. So no, yeah, this was a minimal generating set.
No, but here you have two. Here you have two monomials in each one, right? And which of them goes into the?
So for every element here, the monomial in the first spot is the initial monomial of the monomial ideal.
Okay.
Yeah.
Yeah, I was reading this wrong. And this
is no, sir. Yeah.
And this is which? And this is how do you describe this initial monomial ideal?
Well, from the point of view of cluster algebras, it's the simplest to say that it's generated by products of cluster variables. So all the variables here are cluster variables that never appear in a seed together.
No, but do we have some simple description in terms of Plucker variables? So what, like which monomials belong to the generating set? So it's these. I'm just looking at these monomials. I'm trying to see some pattern here.
Yeah. Well, it's a bit tricky because from the point of view of cluster algebras, these variables x and y, they are kind of as interesting as the Plucker coordinates itself. Like all of them are cluster variables, and you cannot too easily distinguish them. Like there's no.
Okay.
Yeah. And then it gets a bit tricky. And there's not such a nice combinatorial description of the seeds here as we have it for the Grassmannian 2n. One thing to say, but it's not enough, obviously, is that these blue Plucker coordinates that correspond to whose indices are intervals, they can never appear as in leading monomials. That from the cluster point of view is just because they are frozen variables, so they appear in every seed. So for every black Plucker coordinate, you can find, it will, every seed that contains any black Plucker coordinate also contains all the blue ones. So then they cannot be there by this characterization of not being in seed together.
Okay, I think I understand what I was misunderstanding. So it is not true that we have some initial ideal of the Plucker ideal in plain sight here. So it is not, there's no obvious way to pick out a subset of these monomials so that they generate an initial ideal of the Plucker ideal.
Yes, exactly. No, that's a very good point. And geometrically, what you can think of is the Grbner fan of the Plucker ideal and the Grbner fan of this slightly bigger ideal. So we can project from the big one to the small one by just projecting away to the last coordinates that correspond to x and y. But then my monomial cone upstairs does not go to a monomial cone downstairs. There will be some non-monomial elements, and that's exactly because x and y are not monomials in Pluckers, but binomials.
But also, even the Gröbner fan aside, you can, if you just take the ideal and you project x and y to 0, you will not obtain a initial ideal of the Plucker ideal. This is also not true.
Yeah, no, you have to do this elimination theory of intersecting the ideal with the smaller polynomial ring, and then you get the Plucker ideal.
Okay.
But well, you have to substitute x and y for expressions of this form in terms of Pluckers. You cannot set them to 0.
Yeah. Okay.
Yeah.
Okay. Thanks.
Yeah. Well, setting them to 0 would be some initial ideal that happens to be generated only by elements in Plucker coordinates. But yeah, still in the big.
But it's not an initial ideal.
Yeah. Yeah.
Can I ask a naive question? Hi, Lara.
Sure.
So these cluster variables that you find reminds me a lot this exotic cluster structure explored by Gekman, Shapiro, and Weinstein. They found this strange determiner minors, but for matrices which are cut and paste from the initial matrix. And then they found some, I mean, it's amazing what they did. Did you explore the connection with their work on exotic cluster structure on the Grassmannian?
No, unfortunately.
Very naive, I'm sorry, just to know.
No,
because I didn't see
really
the references, so I was surprised.
Yeah, no, I did not. Actually, I'm not familiar with that work. So it's like alternative cluster structures on the Plucker algebra or on the Grassmannian?
Exotic cluster structures on the Grassmannian and on the matrices.
No, that sounds
they
very
have a
interesting.
lot of these kind of formulas here.
Yeah.
And so I wonder, okay, but
cool. So I will have a look. Thank you for the reference.
Sure. Thank you for the nice talk.
Yeah, thank you for listening.
Any more questions? Okay, thank you very much, Lara.
Thank you very much.
Thank you for listening.